Hey guys, this is Group ABLT here making a video about Doppler artifacts. In order to know how Doppler artifacts are present, it is important to know the basics of color and spectral Doppler, along with a little history of Doppler. A physicist from Austria, Christian Andreas Doppler, created the Doppler effect. The Doppler effect is an apparent change in the frequency or wavelength of a wave where there is a relative motion between the source of the waves and an observer. Using the Doppler effect, we can estimate how fast blood flows. Christian Doppler, with this effect, led to many medical advances, including the use of Doppler and ultrasound. And now for the basics of color Doppler. Color Doppler allows you to look at a large region of a patient quickly, giving the mean velocities in a vessel. This is known as qualitative because we are able to know the flow direction, but not the true velocity. It's also important to note that this is the worst for temporal resolution. And now for the color bar. The color bar can be displayed as two different ways, one as BART, or B-A-R-T, and the other is R-A-B-T. BART, which is the most common, and the one used on the slide here, is blue away and red towards. R-A-B-T is just the opposite. Wall filters are also shown on the color bar, and this is just the black middle line that separates the red from the blue. Wall filters are high-pass filters, which means that velocities that pass are higher than threshold. They reduce the amplitude of the low-frequency shift signals. And now for color gain. Color gain, or sensitivity of color, amplifies signals in the receiver. It uses a color noise threshold. This means that a pixel is either displayed as color or not. The goal for color gain is to have it as high as possible without causing speckle. In this image here, it demonstrates undergain, overgain, along with optimal. The undergain just means the gut gain is set too low where there's not enough color. Overgain is set too high where it's showing color outside of velocity regions. And the optimal gain is the best color gain for this image. And for the basics of spectral Doppler. Spectral Doppler is very important to get the right Doppler angle. The Doppler angle is the insonification angle, and this is the angle between the observer's line of sight and the direction the source is moving. If you have an incorrect angle, this can lead to Doppler artifacts and Doppler error. Some different examples of angles on this slide are 180, 0, and 45. The 180 degrees angle, the source is moving directly away, the 0 is moving directly towards, and 45 it's moving towards, but at an angle, as you can see, of 45 degrees. The best angle for Doppler is to be between 45 and 60 degrees. This image just demonstrates the 60-degree angle to the vessel when using Doppler. 90 degrees would show velocity of 0, since the cosine of 90 is 0. No blood is going towards or away at this 90-degree angle. An incorrect angle will lead to incorrect spectral information.
Okay, moving on now to spectral basics. So Doppler measures blood velocity, and velocity measurement is accomplished by tracking the frequency shift from red blood cell echoes. Before exploring artifacts related to spectral Doppler, I thought it was really important to understand how spectral Doppler extracts data, and I thought it was best to do this, to illustrate this, by comparing it to color Doppler. So color Doppler is an estimate of mean velocity. It does this by using the Doppler effect. It then factors in frequency shifts and then creates a mean flow velocity. But because of this, it doesn't provide peak velocities, and it's also scanned. Spectral Doppler, basically the complete opposite. It provides information along a specific line, and it provides peak velocities because of this, and it's also non-scanned, which becomes important later. So colored, again, just reiterating what I said, color Doppler is able to assess very large areas of interest, whereas spectral allows assessment at pinpointed areas. So virtually all spectral artifact is a result of a velocity measurement error, meaning velocity is usually over or underestimated. And it's usually due to an incorrect direction sample or value, meaning that the sample angle can be incorrect or the scale might be too high. This error presents itself, of course, it only makes sense, as an inaccurate representation of Doppler flow. And there are two interrogation methods to investigate Doppler shift within a vessel. You can either use pulsed wave or continuous wave. Okay, and now we're ready to move on to the artifacts. This is just a general overview of some of our artifacts. We have aliasing and range ambiguity, spectral mirroring, spectral spread, blossoming, and wall filter saturation. So our first artifact, and the most common by far, is aliasing. And there are pros and cons to using continuous wave versus pulsed wave. So continuous wave is more sensitive and won't ever cause aliasing, but there's also no depth resolution. Whereas pulsed wave is much less sensitive and so much more susceptible to aliasing when it comes to high velocities, but there is depth resolution. Another one of our artifacts is range ambiguity, and range ambiguity can be caused by a high PRF. This becomes an issue when another pulse is sent out before all of the previous pulse echoes have been received. This causes basically a blurring of information. It causes early and late echoes to be received at the same time, and this leads to incorrect data. In pulsed wave Doppler, it's ever present. Pulsed wave Doppler always receives multiple gate echoes. It becomes more problematic at shallower depths because there may be no flow at one of the gate locations, and ambiguous gates placed at shallower depths, of course, can interfere with the data. So to overcome this or determine if range ambiguity is actually the problem, you can just change the PRF. So changing the PRF changes the PRP, which changes the actual physical location of the gate. If range ambiguity is actually the problem, then the waveform characteristics will be altered.
Okay, the next thing we're going to talk about is artifacts that show up both on a spectral and on a color Doppler image. The first thing we'll be talking about is aliasing. You can see in the picture both aliasing in a color image and on a spectral image. This occurs when the Nyquist limit is exceeded, there's insufficient sampling in a particular area, angles closer to 0 or 180, or as you can see in the image, in the center of the vessel where the flow is fastest, as well as any bends and curves, and this can be corrected by the sonographer. All we have to do is increase the scale, change to a lower frequency transducer, switch to continuous wave Doppler, or we can just move the baseline down. Aliasing can occur both with a color image and with a spectral image. You can see in the color image the baseline wrapping around from the top to the bottom. It goes from red to yellow to blue, so we have to increase the scale to correct for this. The next thing we're going to talk about is turbulence. This is a disturbed flow state. It's pathologic. As you can see in the image, we have laminar flow versus turbulent flow. Laminar flow is all the same direction, and turbulent flow is kind of going in all different directions. This often occurs as blood leaves the stenosed area. The Reynolds number is used to determine the likelihood of turbulence. If you have a high Reynolds number over 2,000, you're likely to have turbulent flow. This cannot be corrected by the sonographer because this is a pathologic state. And here are some images, examples of turbulence. Now I'm going to talk about blossoming. Blossoming is caused by overgaining the spectrum on a color or a spectral image, also caused by too high of a transmit power. This signal, as you can see in the top image, bleeds over into the neighboring regions. Peak systolic velocities are artificially high, as you can see in the bottom image, and this can be corrected by decreasing the gain.
So, another artifact to talk about is mirroring. We have spectral mirroring and color mirroring. So mirroring is a mirror image of the Doppler spectrum produced on the opposite side of the baseline, as you can see it here. So that's the real image, and that's the spectral mirroring. It occurs mostly if the transmit power is too high, if the receiver gain is too high, and to correct that, we can lower the gain. Superficial vessels integrated with too high frequency transducer. If angles are close to 90 and We change that just if we angle away from 90 degrees, and if we have a poor system design. We have also color mirroring. So it's the same as spectral mirroring. There's a mirror image down the real image. And mirror image artifact can be detectable when there is a high spectral reflector like a bone. As we can see here, there's a subclavian artery, and then we have the clavicle bone that is a high spectral reflector, and we have the artifact image. It also occurs in stenosed vessels when strongly reflecting plaques on the wall of the vessel distant from the transducer head were isonated obliquely. Another artifact is spectral broadening, which is also known as spectral spread. So it appears as overestimation of the peak velocity, and we have a fill end of spectral window. We have two types of spectral broadening. It could be real, and it occurs due to many different velocities within the sample gate. As we can see here, we have real spectral broadening that is caused by turbulence in a vessel. We have an artifactual spectral that is occurred because angle to flow from each crystal element in an array is slightly different, causing slightly different Doppler shift frequencies recorded. We have here because we have a large gate size that caused that broadening. It can be corrected by changing the angle to less than 60 degrees. Well filter saturation. Well filter saturation is a clutter signals that are not adequately attenuated by the well filter. The dynamic range is too large, causing circuit saturation. So we can see it, circuit saturation. It appears as a vertical bright band repeating at predictable intervals across spectrum, producing a characteristic thumping noise. To correct it, we need to set well filters appropriately.
Now we're going to do a quiz. If you need to pause the video, you can. What kind of artifact can be corrected by the sonographer? If you need to pause to think about it, there are a couple of answers, but I'm going to go ahead and give them to you now. Aliasing, blossoming, wall filter saturation, spectral mirroring, and artifactual spectral broadening can be corrected by the sonographer. What kind of artifact is this? This is spectral mirroring. What artifact do each of these images demonstrate? The one on the left is aliasing, the one on the right is turbulence.
Thanks for watching. We hope that was helpful and helped you guys for a better understanding of artifacts as they get mixed up a lot.